Hello everyone. The title of our group's project is Facial Emotion Recognition. We are working on a facial emotion recognition machine learning project using the PyTouch framework. This project aims to train a machine learning model that can recognize emotion state from given facial images using the VGG19 convolutional neural network, calculate accuracy, and attempt to complete the training and compare accuracy differences using different type of data set. Below, I will discuss how the training was conducted. The first part to introduce is about the data pre-processing process. As we know, pre-processing is an essential step that we use to clean and optimize data to fit the model. Through pre-processing, we can make our model understand the data better and identify facial expressions more accurately. This is especially crucial for emotion recognition tasks. In our code, we first define some path variables to find images of emotion categories stored in different folders. These images have been classified into 7 basic emotions: anger, disgust, fear, happiness, sadness, surprise, and contempt. We choose PyTorch as a deep learning framework and build a convolutional neural network model. PyTorch is a feature-complete framework used for building deep learning models, commonly used for machine learning applications such as image recognition and language processing. The unique feature for PyTorch is that it fully supports GPUs and can dynamically modify computational graphs. We use the classical VGG and cross-entropy loss function for model training, with a stochastic gradient descent optimizer used to adjust the model parameters. Through dividing the data into training and testing set, loading the data and performing batch processing. In the field of data science and machine learning, HDF5 files are often used to store training and testing dataset. They can store a large number of data samples while maintaining high read and write speed, which is crucial for training complex machine learning models. First, we create two empty lists, data X and data Y, to store our image data and the corresponding labels. Next, we begin to read images in the folder of each emotion category. The image file names are sorted to ensure that the training set does not conclude the test set to prevent our model from overfitting during the testing phase. We read each image as a grayscale image, which can reduce computational complexity while maintaining important image features. After each image is read, we add it to the data X list, and the corresponding emotional label is added to the data Y list. For example, for image stored in the anger directory, we add a label of 0. For image stored in the disgust directory, we add the label of 1, and so on. After completing this step, we will print out the shapes of data X and data Y to ensure that our data has been loaded correctly. Finally, we save data X and data Y as HDF5 file format. The last 4 lines of code create a dataset named data_pixel in the data_f5 file and store the data in data X into the dataset for storing pixel values for images, and a dataset named data_label and store the data in data Y into this dataset for storing corresponding category labels.
Next, the script defines the training and testing functions. The training function obtains the predicted results through forward propagation of the input data and targets, calculates the loss, and then adjusts the model parameters through backpropagation. Here, an epoch represents training ones on the entire dataset, and this project stipulates that one training run lasts for 60 cycles. This code in the first red box here represents at the beginning of each new cycle of training. First prints out the current training cycle number, then sets the model to training mode, and initialize the training loss, the number of correctly predicted samples, and the total number of samples to 0. This code in the second red box here primarily handles the decay of the learning rate. In this project, this means that starting from the 21st cycle, the learning rate for each cycle will decay to 0.8 times the learning rate of the previous cycle. The new learning rate is then used to update the optimizer's parameters. This code in the third red box is the core of the training process. It iterates through the training data, calculates the difference between the model's predicted results and the actual results, and uses this difference to update the model's parameters. The training data is passed to the train loader in batches, and we have previously stipulated that each batch contains 128 pieces of data. The batch index represents the current batch of data being fed in. First, we use optimizer.0 to clear all optimized gradients. Then we feed the data into the VGG19 neural network for first rough training, get the predicted results, and use the predefined loss function to calculate the loss rate between the predicted results and the actual results. Then loss.backward is used to calculate the gradient of the loss function with respect to the model parameters. Before using optimizer.step to update the gradient of the model descent, we first perform gradient clipping .clip gradient to prevent gradient explosion. The remaining of this function counts the current training cycle's loss and accuracy. It calculates the cumulative loss for all batches within the current cycle. The touch.max method returns the index corresponding to the maximum probability that the graphic summary belongs to a certain class of emotion. Total stores the total number of all samples. Then we use a Boolean statement to return the value of the correctly predicted images as 1. Add up the number of correctly predicted images and store it in the correct variable. We use a progress bar to display the current training progress and print the average loss rate and accuracy, the number of correctly predicted pictures and the total number of the dataset for this cycle. The accuracy of this cycle is saved in the train_ec variable. The difference between the test function and the training function is that the test function iterates over the test loader loaded with the test set. The test function needs to first convert the data into a four-dimensional tensor. For example, discard the uncropped dimension so that the data can be fed into the neural network. Because we processed a single image 10 times, we need to make predictions for each of the 10 parts belonging to the same photo. Add the 10 prediction results and take the average to get the probability of the original data belonging to each category. This last section of code is for updating and saving the best accuracy of this training run, the corresponding best cycle number, and the operation of saving the model. Finally, the script loops through training and testing until the specified total number of training runs is reached, and then prints out the highest accuracy of the test set and the corresponding cycle number. Lastly, we use Python's visualization libraries to judge the probability of different emotional categories of the input image using the trained model and generate images as results.
Firstly, we used the CK Plus dataset, which showed a total of 981 photos with a size of 3.83 MB. Each image had a resolution of 48 times 48 pixels, all in black and white. After converting the dataset into an array and storing it in the H5 file, the dataset size is 2.16 MB. The test set of the modeling train through this dataset has a maximum accuracy of 93.94%, corresponding to the 26th epoch. We import the photos of our classmate into the model, get the probability that the import belongs to each emotion, and use Python's visualization library to output. We can see that the first student's output is correct, and the model gives him a very sad conclusion, but the second student's output is wrong. We can clearly see that his emotion is happy, but the final output is almost sad. So we decided to use another dataset. We then went on to find the AffectNet dataset on GitHub, which had a total of over 30,000 photos, all in color, each with a different size and high resolution. We wanted to train directly with the dataset, but we failed due to device configuration. So we reduced the number of photos to 2,100 and trained again. These photos were 97.4 MB, and after image processing, the H5 file was 4.63 MB. Unfortunately, the accuracy of the model trained through this dataset is very low, as we can see in the figure that the highest accuracy is only around 17%, and the same import result in even more serious error. And we can see that the probability of each emotion was here is very high, just like a rainbow. So this training was a complete failure. Finally, we choose a dataset on Kaggle, which contains over 28,000 photos in the same format as the first CK Plus dataset, which is 48 times 48 pixels in black and white. The dataset size is 112 MB, and the final H5 file size is 63.3 MB. The final test set accuracy was 71%, and in subsequent multiple training, it reached a maximum of 82.46%. Looking at these two input again, both output have become correct, the first being sad and the second being happy.
The conclusions drawn from training and testing different datasets to achieve higher model accuracy are as follows. First, try to choose datasets with less irrelevant background in the pictures. Second, the accuracy of the model does not depend on the size of the dataset, but on the parameters we assign to the model, such as batch size and the learning rate and so on. And third, the amount of data loaded into the train and test loaders needs to be repeatedly adjusted, as shown in the figure. A confusion matrix can be used to judge the weight of the data to be fed into each category. And here are our references. Thank you for listening.